So let us continue with problems that will present applications of heat transfer to energy science and technology. You know that in majority of systems where we have to ensure heat exchange, we need to do appropriate design of heat exchangers. And let's say, for example, in solar applications, heat exchangers are used a lot. And the design is based really on understanding well heat transfer process and in writing the corresponding equation to be able to optimize the design of the heat exchanger. So here we give an example. As you know, if you have any idea that is new, I will give you in the problem all you need to solve. Okay. So for example, if you remember last time, we considered the case of heat transfer through a plane wall, and I gave you the resistance to conduction in a plane wall. So in case, for example, I have a new geometry like in this case here. In this case here, you have like cylindrical coordinates because the shape of pipes is it's a tube, so it's a circular cross section. Okay, and let's say you have like a the tube will have a certain thickness, and in general in heat exchanger we have one fluid, let's say, that is coming from the inner side, and another fluid that is getting from that is going over the outer side of the circular tube. And we can have several scenarios. We can have parallel flow or counter flow. So from the design consideration, we can decide, depending on what we need, what is the best configuration to use. Okay. So here they are telling us that in order to design a heat exchanger, they gave us first that the resistance form in cylindrical coordinates is given by ln R out over Rn over 2 pi Kl. So if you have a tube, okay, and you have the sorry, you have the inner radius and the outer radius. So this is R inner from the inner side, and we have R outer from the outer side. So within the tube, heat is transferred through the tube thickness by conduction, while from the inner side you have a fluid moving, so heat is transferred to the tube by convection, and from the outer side, from the surface to the outer fluid, you have also convection. So that's why here, if you want to do the analysis, we have three resistances. And this will allow us to draw the thermal circuit as we did last time. Because what will happen, consider, for example, that the average temperature of fluid A is larger than the average temperature of fluid B. So heat will flow from A towards B, okay, to the external environment. So we can say that if we want to draw the thermal circuit first to be able to deduce an expression of the rate of exchange, we start with the highest temperature. Let's say we know the temperature of fluid A. So the first type of resistance from fluid to surface is by convection. So the first resistance that we will consider is resistance to convection, and we have seen together last time that this resistance is of the form 1 over convective coefficient. So here we have convection from inner side times, of course, the area of the inner side. The area of the inner side is the exchange area. You know that if you have a pipe, if you have a cylinder, the area of exchange is the lateral area. The lateral area of a cylinder is the perimeter, 2 pi r, times the length. So we can replace AI by 2 pi times R inner times the length of the tube, okay? Times up. So this is for the convective resistance. Now, next step, heat is conducted through the tube material, which is a solid. So we need to consider now the resistance to conduction. And they gave us the expression. Yeah? You are not supposed, of course, to know these formulas. I will give you the formulas, you just have to apply them. So it's unlike plane wall. In plane wall, the resistance to conduction was L over Ka. However, in case of cylindrical coordinates, it's logarithmic. So we have to consider always L ln R out, yani the big radius, over the inner one. So ln R out over Rn divided by 2 pi KL. K is the conductivity of the material. So over 2 pi K, where K represents the conductivity of the tube material. And we multiply by L, which is the length of the duct. So this is the resistance to conduction. Finally, the final resistance is a resistance to convection. So when you go from the surface to the outer fluid, the type of resistance is convection. And the resistance to convection is similar to this one, but now instead of taking H from the inner side and area from inner side, so we consider H out, A out. Okay, so this will give us the thermal circuit. Once we draw the thermal circuit, we are ready to calculate the rate of heat transfer. And you know that in this application, we need to maximize heat transfer. In general, heat exchangers are used to transfer heat from one fluid to the other, or from one place to the other. That's why when we do the design, here we need to minimize the total resistance. So the objective is to maximize heat transfer. We want to increase Q by reducing the resistance. So we can work here on several factors. We can enhance the convective coefficient. One strategy, for example, is to have, let's say, higher velocities of the fluid. We can increase the area of exchange by proper design of the area needed in our heat exchanger. We can select a convenient tubing material. So we can have, of course, we should have high conductivity. A high length also will favor reducing the resistance. So all of these parameters can be studied. So whenever we talk about the design of a heat exchanger, we can investigate how to vary these parameters within a possible range, of course, in order to enhance heat transfer between the two fluids. And then, depending on our application and the amount of heat transfer we need, we can select the appropriate heat exchanger to use. We have, of course, several types of heat exchangers. And one of, if you want, in research, especially with solar system, we can work on several designs depending on the application. So we'll see when we study solar energy that if your application, for example, is to heat, if you want to heat, let's say, water for swimming pools, you don't need to reach a very high temperature. So you can use a simple design of heat exchanger. But if you want to use a heat exchanger for domestic hot water needs, you know that for shower, for example, we need to have a high temperature of hot water to kill a certain type of bacteria. So you need to increase the temperature to a high extent. That's why you need to come up with a more complex design of your heat exchanger and another type of heat exchanger. So that's why it's very important to understand this mechanism of heat transfer, because they will help us to do appropriate design for a certain application. Okay. So now, whenever we have the expression of the flow rate, okay, we can do a parametric study to optimize the design to maximize the heat exchange. Now, they are asking us also not only to express the flow rate function of the resistances and the temperature difference, delta T, but also we want to express it function of the inlet and outlet temperature of fluids A and B. Here it's to be noticed that as the fluid A is moving through the heat exchanger, its temperature will decrease while TB will increase. That's why if you want the computation, this delta T here is not straightforward. It's not a constant. And in realistic calculations, they do the analysis for a small control volume. Of course, we'll not go through these details. We care for, if you want, the overall view of the problem. But this parameter delta T overall, if you want, is calculated by integration. And of course, you are not responsible of getting it. So I will give you the expression of delta T overall, okay? As we'll see in next problem. But what you should know is that this total heat rate Q can be expressed also function of inlet and outlet conditions of your fluid. Because if you remember when we discussed several types of heat, we said we can work with sensible heat, we can work with latent heat. Whenever we have change of phase, we talk about heat transfers through latent form. However, here in this heat exchanger, heat is transferred by sensible form. You have variation in temperature. So since we know that Q sensible is MCP delta T, okay? And whenever we talk about Q in this form, let's say it's in joule. When we say MCP delta T, it's in joule. But if we want to express it in joule per second, yani per unit time, then instead of having M, we talk about M dot. So if we want to have it in joule per second, then it's Q dot, it's M dot CP delta T, okay? So here we can find by second, in joule per second, what is the heat rate of exchange. We can consider fluid A or fluid B, because you know what is lost by A will be gained by B. If we assume, of course, negligible heat losses to surrounding. So assuming no losses, what is the heat that is lost by A will be gained by B. And therefore, we can write the following equation. We can say that the rate of heat lost by A can be expressed as mass flow rate of A times the specific heat of A times T inlet of A minus T outlet, okay? While for B, we'll take the opposite, T out minus T in, because what is happening is that the temperature of A is decreasing because heat is lost by A, while the temperature of B is increasing since B will gain heat. So this heat in absolute value, this heat exchange is M dot Ca Ta1 minus Ta2 equals to M dot Cb Tb2 minus Tb1. So this will allow you, for example, if you want to reach a certain temperature of Tb, you need to reach a certain value Tb2. This will allow you to decide what should be the mass flow rate of A to use, or what should be, if you want, the inlet temperature. So depending on the problem, sometimes you have parameters that are fixed while you can play with others. So this equation will help you in your design to decide on the mass flow rates, to decide on the inlet temperatures, etc. Okay. Any question on this? Okay. So let us continue with another problem. We'll still in same application of heat exchangers, but we'll discuss now more details of design. Okay. So as we mentioned, if as I said, you have several configurations. So if I consider ecocentric heat exchanger, I have, as we mentioned, you have a tube, you have one flow through the inner side and another flow from the outer side, okay? And we can have two configurations, parallel, so the two flows will have same direction and same sense, and counter will have opposite sense. In general, the counter configuration is more efficient, and we'll discuss why. And in this case, as I told you, if you want to compute the heat rate, you have several ways. Or you get the overall heat transfer coefficient U. If you remember how we determine this coefficient, UA is 1 over the total resistance. So 1 over sum of resistances. This is how you get the overall heat transfer coefficient. And it's defined relative to a certain area of exchange. While, as I mentioned for you, delta T is computed by integration. So it's like an average value. And this will be given to you. You don't have to go through details of integration. I will give you the formula, okay? So I will tell you that one way to calculate your heat rate is to consider 1 over summation of resistances, which is equal to U times A, times delta T logarithmic, okay? And this delta T is given by the following expression. It's delta T2 minus delta T1 over ln delta T2 over delta T1. What do we mean by delta T2 and delta T1? So here we are explaining everything for you, okay? You have two fluids, a hot fluid and a cold fluid. So let us take the first scenario of parallel flow, okay? So this is my tube. And I have section 1 at the inlet, let's say, okay? So I have, this is section 1, and this is section 2. And I have two fluids that are moving in same direction, same sense. One from the inner side, one from the outer side. If I talk about the parallel configurations, at section 1, I have inlet for both fluids, okay? So the formula for delta T1 is, let's say this is the hot fluid, for example. So I will call this temperature T hot 1 and this temperature T cold 1. Since both are inlets, T hot 1 minus T cold 1 is the difference between the inlet temperatures, T hot N minus T cold N. While delta T2 is the difference in temperature at the exit, at section 2. So here also, the two flows are same sense. So I do T hot 2 minus T cold 2. And of course, okay, what will happen here is that the temperature of the hot fluid will be reduced, okay? And the temperature of the cold fluid will be increased, but always, okay, you will have that, so the difference in temperature between the two is reduced as you go through the heat exchanger, okay? And it's impossible if you want to have, always the temperature at the outlet here, okay, should be at the outlet of cold fluid is smaller than the temperature of at the outlet of the hot fluid, because you always have this heat transfer in this direction. The temperature of hot will always be larger than the temperature of cold. On the other hand, in counter configuration, we have a different profile, okay? Because what will happen in this case is that at section 1, you have, let's say, inlet of hot and outlet of cold. So you will have TC1 will represent, let's say, T cold out, okay? While TC2 will represent T cold in. And because of the heat transfer that is happening, okay, you have that T cold will increase, T hot will be reduced, but since at this level, at the exit of the cold fluid, you have heat transfer with the hot side, the inlet side of the hot fluid. You might have that the cold fluid temperature at outlet is larger, okay, than the hot fluid at outlet, because here the condition to maintain heat transfer is to have T hot larger than T cold, but T hot at inlet. So T hot at inlet is larger than T cold outlet, but this does not require that T cold out should be smaller than T hot out. And this profile will allow you to maintain a higher temperature difference delta T at the end of your heat exchanger. That's why in general, the counter configuration will be more efficient. Okay, and you can study the effectiveness of this heat exchange by doing the ratio of the actual heat transfer that is taking place in the heat exchanger to the maximum possible heat transfer. So as I told you, you can be in front of a new problem, but with all of these formulas given to you. You just have to apply your knowledge, which consists on knowing how to put energy balances, how to write the rate, okay, how to put the thermal resistance circuit to be able to calculate, let's say, the overall heat transfer coefficient Q, which is related to the resistances. So you should know how to build the thermal circuit, how to apply these formulas, and how to apply formulas of heat transfer. In case of sensible heating, let's say, you can write Q in this form, but at the same time, you can say that it's equal to m dot of fluid A times the specific heat of fluid A times delta T of this fluid, okay? The same for B. So if you use these relations, you will be able to solve for the unknowns in your problem. And we'll see now an example of this, okay? So let us consider the following given. So we have a concentric tube heat exchanger with an area of 50 meters square of heat exchange operating under the following condition. So we have two fluids, as we mentioned. We have, as we said, a hot fluid and a cold fluid, and they gave us the properties needed for calculation. We know the heat capacity of each fluid. Please pay attention for unit. Okay, so here, when they give you the unit in kilowatt per Kelvin, this means that they gave you big C, okay? Because look, what is, we know that you have Q is m dot, small m dot, times small c, times delta T, okay? So if you use this formula, if you do unit analysis, you have the heat rate in watt, and you have delta T in Kelvin, okay? So m dot C will represent for you, the unit of m dot times C is watt per Kelvin, okay? Or it can be in kilowatt per Kelvin. So if I give you Q in kilowatt, then m dot C is in kilowatt per Kelvin. So you know from the unit provided here that they didn't give you the small c, heat capacity small c. They gave you this capacity multiplied by the mass flow rate of the fluid. And now, if you want to compute, let's say for the hot fluid, the heat rate, it's equal to big C, that is given here, okay, times the variation in temperature, delta T. So for the hot fluid, the temperature will decrease. So delta T will represent Tn minus T out of hot. So Tn hot minus T out T out of hot. And to differentiate between hot and cold, I will put here C hot, okay? While for the cold fluid, since we assume no losses, so what is lost by hot fluid is gained by cold fluid, we can say that this is equal to the heat that will be gained by the cold fluid. So it's big C of cold fluid, okay? And now since the temperature of the cold fluid will increase, it's T cold out minus T cold in. So already, okay, as you can see, they gave us a big C of cold and hot, and we have all temperatures except one temperature. The only unknown temperature is the temperature at the exit for the hot fluid. So this equation, this energy balance, which consider that heat lost by hot fluid is gained by cold fluid, will allow you to find your unknown temperature. So this is a first step to get our first unknown, which is the outlet temperature of the hot fluid. Okay. Now, to know if the heat exchanger is counterflow or parallel flow, we know that if it's parallel, it's impossible that the outlet cold temperature cannot be higher, okay, than the exit temperature of hot fluid. In case it's higher, then it's of course counterflow. So let us look at numbers to be able to answer this question. So as we said, the first step is to apply the energy balance. And from our energy balance, we can get the temperature at the exit of hot fluid, okay? And we can present this if you want in a graph. So we have for the hot fluid, the inlet temperature was 60 degrees. And from our calculation, the outlet temperature is 48, which is smaller than the outlet temperature of the cold fluid. And this is only possible, as we discussed in the design, in case of counterflow configuration. Because what will happen here is that for your hot fluid, the temperature will be reduced. For your cold fluid, the temperature will increase. And always, to allow heat transfer to be possible, at any section, the hot temperature, of course, the hot fluid will have a temperature larger than the cold fluid. But because of this counterflow configuration, it's possible if you compare T cold out, it can be larger than T hot out, which is the case in this example. But it should be smaller than, of course, T hot in. While if you draw the parallel configuration, okay, then you have the same direction for both flows. Then what will happen is that you will have a high delta T first, and this delta T will be reduced as you go through the heat exchanger, and always you will maintain a hot temperature, TH, larger than T cold. So of course, at the outlet section, T hot out is larger than T cold out. While here, at the exit of the cold fluid, you have heat exchange with the inlet of the hot one. So there is no condition that the outlet temperature of the cold fluid should be smaller than T hot out. It's not necessary at all. It can be, but in this case, you are sure that because it's larger, you are sure that you don't have a parallel configuration, you have a counter configuration. Okay? If it's smaller, you cannot judge. So you need extra information to be able to know if it's counter or parallel. Okay? Any question on this?
Professor, parallel بيمشوا سوا وcounter بيمشوا عكس بعض.
Yes, exactly. Exactly. Okay. So this is for the first question. So we were able to get the temperature, and we were able to determine if it's counterflow or parallel flow. Next step, they want us to find the effectiveness of our heat exchanger. Okay, so to answer this question, the effectiveness definition is given. So I gave you here what is the definition of effectiveness. If we go back to the formulas, The effectiveness represents the actual heat transfer over the maximum possible heat transfer. Okay? So first, to be able to answer this question, let us think together what is the maximum possible heat transfer. We know that heat transfer is calculated as big C or m dot C times delta T. Okay? And you know that the biggest temperature difference, okay, will be for the fluid having the smallest capacity, because if you write your equation, so let's say C cold times delta T cold, and delta T here in absolute value, highest minus lowest, okay, equals to C hot. So this is from energy balance, as we said, neglecting any loss to surrounding. So this is our condition of energy conservation. So the fluid that will experience, if you want, the highest delta T. So delta T is maximum for the fluid that is characterized by the smallest heat capacity big C. Okay, so first we can say that what is if you want to do analysis, what is the maximum possible delta T? Actually, you know the temperatures. Okay, you at the inlet, you know T hot in and T cold in. Okay, so you know that the difference will be the largest possible difference is between inlet temperatures, because what will happen is with heat exchange, the inlet temperature, the temperature of hot fluid will be reduced and the temperature of cold fluid will increase. So the highest possible value of delta T, okay, is the difference between inlet temperatures. So this is the largest possible gradient. This is why, in order to find what is the maximum heat transfer, we select the minimal heat capacity and we multiply it by the difference in temperature at inlet condition, which is the maximum possible delta T. Now, the actual heat transfer, so effectiveness is actual over maximum. The actual heat transfer is the rate Q that we know how to calculate. So Q is UA delta T, okay? And here I provided you with the formula. So you have to just to apply this formula to get delta T logarithmic. You apply this, and as we said, depending if parallel or counter, the formula will change. So here, since we have counter configuration, we should adopt the following calculation. For delta T1, it's T hot inlet minus T cold outlet. And for delta T2, it's T hot out minus T cold in. We have everything. We have calculated the missing temperature. So we can evaluate delta T1 and delta T2. And once we have them, we just have to plug in this formula to get the expression of delta TLM. Now, for the overall heat transfer coefficient, or it will be given directly for you, or like in the previous problem, okay, they give you the design of the heat exchanger, and you know by definition that U times A is equal to 1 over summation of resistances. So if we have an example similar to the previous one, in the sum of resistances, we should consider resistance of convection from the inner side plus resistance of conduction plus resistance of convection from outer side. Okay? If they don't give you details, they should give you then the value of U. So they give you U or U times A. Okay? So if we go back to this problem, okay. Here, if you want, or if they didn't give us U, okay, and we want to use another formula for Q, then we know that Q can be calculated by several ways, or UA delta T, okay? So you can use this formula in case you have U and the area, or also you can use, as we mentioned at the beginning, Q can be calculated in two ways, or m dot Cp, so big C if you want, of the hot fluid, okay, times T hot in minus T hot out, and we have already all temperatures, okay? So you can apply, to get Q, you can apply the formula or on hot fluid by doing CH T hot in minus T hot out, or also you can evaluate Q by doing C cold times T cold out minus T cold in. You have all temperatures, so you can select the part that you want. And now, once you have Q, they can ask you in a reversed way. They can ask you to deduce the overall heat transfer coefficient, because we know these two terms can be evaluated, so we can evaluate Q. And then we have delta T according to the formula that we discussed, delta T logarithmic, we can calculate it. They gave us the area, so now we are ready to calculate the overall heat transfer coefficient U, okay? And of course, to get the effectiveness, all we have to do is to divide the actual heat exchange by, as we mentioned, the maximum possible heat exchange, which is C minimum, times the maximum delta T possible, which is T hot N minus T cold N. In this way, we can calculate the effectiveness of our heat exchanger. And also we are able to calculate the overall heat transfer coefficient U. And we can do a parametric study. What are the parameters that should be varied? For example, if we want to increase the effectiveness, how this will